And now, in the velvet hush of the night, we drift together, gently, into the immensity above us. Look upward, if you will, through the imagined roof of your quiet room, past the familiar tiles and timbers, past the slow-turning air of the earth itself, until the sky opens like a vast, dark sea. There, suspended in the winter or summer constellations, whichever season cradles you tonight, lies the faint, luminous river we have known since childhood, the Milky Way. A pale band of light, soft as breath on glass, arching from horizon to horizon. For generations we have called it home. Yet tonight, dear companion of the dark hours, we must confess something rather startling. The galaxy we thought we understood, the galaxy we believed weighed a comfortable 100 billion times the mass of our sun, has quietly, almost politely, doubled, tripled, and then redoubled itself while we were looking the other way. The true mass of the Milky Way, according to the latest and most exquisite measurements, is not 100 billion solar masses. It is closer to 1.5 trillion, 1,500 billion suns, a figure so colossal that it rewrites every textbook, every lecture, every quiet fireside certainty we once possessed. And we, lying here beneath our blankets, are embedded somewhere near the outer suburbs of this scarcely imaginable leviathan. Let us linger on that number for a moment, as one might linger beside a cathedral door before stepping inside. 1.5 trillion solar masses. If we were to count one solar mass every second, never sleeping, never pausing, it would take us nearly 48,000 years to reach the total. 48 millennia of ceaseless counting merely to name the weight of the galaxy that cradles us tonight. And this is no idle speculation, no theoretical flourish. This is the measured, peer-reviewed, almost embarrassingly robust conclusion of the past half-decade of astronomy. Only 15 years ago, in the gentle pre-dawn of the 2010s, the consensus was comfortingly modest. The Milky Way, we were told, contained perhaps 200 to 400 billion stars for every 100 billion solar masses of total material. Visible stars, we thought, accounted for roughly 60 to 100 billion solar masses. The remainder was attributed to dim red dwarfs, to the cold gas between the stars, to the dark matter that refuses to shine. 100 billion, perhaps 200 billion solar masses in total. A respectable galactic mass, certainly, but one that placed us in the middle ranks of the cosmic hierarchy, larger than the small Magellanic Cloud, smaller than Andromeda, comfortably average among the great spirals. We slept easily beneath such a sky. Then came the revolution, quiet at first, almost courteous, like a visitor who removes their shoes in the hallway. In April 2018, the European Space Agency released the second data release of the Gaia spacecraft. Gaia, that tireless celestial cartographer drifting at the L2 point, had spent years staring at more than 1 billion stars with a precision that would have seemed sorcerous only a generation earlier. It measured not only positions, but proper motions, the slow sideways drift of stars across the sky, and, for many, line-of-sight velocities as well. Suddenly, we possessed, for the first time, a three-dimensional velocity map of a significant fraction of the Milky Way. And velocity, as every schoolchild once learned and then promptly forgot, is the key that unlocks mass. For in a galaxy, just as in the solar system, objects orbit according to the gravity that binds them. The faster a star moves at a given distance from the center, the more mass must lie within its orbit. This is Kepler's third law, writ large across 100,000 light-years. Yet for centuries, we had been forced to guess. The Sun lies roughly 26,000 light-years from the galactic center, far enough that most of the mass lies inside our orbit, close enough that local complications cloud the view. Stars near the Sun orbit at approximately 220 kilometers per second, a speed we had measured since the 1920s. But was that speed maintained far beyond the Sun? Did the orbital velocity curve fall away gently, like the planets beyond Neptune, implying a modest total mass? Or did it remain stubbornly flat, demanding ever more invisible mass to keep it so? The old data hinted at the latter. As early as 1978, Vera Rubin and her colleagues had shown that rotation curves in external galaxies refused to decline. But for our own galaxy, the evidence was maddeningly indirect. Radio observations of hydrogen gas, infrared counts of bulge stars, the motions of globular clusters orbiting far above the plane. Each tracer told a slightly different story. By the year 2000, the range of published estimates for the total mass within 50 kiloparsecs, roughly the visible disk, spanned almost an order of magnitude, from 300 billion to nearly 2 trillion solar masses. The textbooks, anxious for consensus, settled on the lower end. 1 trillion solar masses became the cautious upper limit. Most authors preferred 5 or 600 billion. Then Gaia began to speak. In 2019, using only the early DR2 data, a team led by Amina Helmi and her collaborators at Groningen examined the motions of several million stars beyond 30 kiloparsecs. To their quiet astonishment, the rotation curve remained almost perfectly flat out to twice the Sun's distance from the center. In 2021, using the more complete early data release 3, Macmillan and his colleagues refined the potential of the Milky Way and derived a total mass within 100 kiloparsecs of approximately 900 billion solar masses. Still cautious, still, one sensed, underestimating. The true revelation was delayed by the pandemic, by careful checking, by the sheer difficulty of modeling a galaxy that contains not only stars and gas, but an ancient accretion record written in the orbits of shredded dwarf galaxies. Yet piece by piece, the evidence accumulated. Hypervelocity stars flung outward by the central black hole were found to be moving too slowly to have escaped a shallow potential well. The orbits of the Magellanic Clouds, our nearest galactic companions, demanded a host mass exceeding 1 trillion solar masses simply to keep them bound. The timing argument from the Sagittarius dwarf, torn apart over billions of years, suggested an even heavier Milky Way to explain the length of its tidal streamers. And then, in the closing months of 2025, the fourth full data release of Gaia arrived like a tide that had been gathering far out at sea. DTAR 4 contains precise distances, proper motions, and radial velocities for nearly 2 billion stars, together with astrophysical parameters for 500 million. The statistical power is almost indecent. Where once we had perhaps 10,000 stars with full 6-dimensional phase space information, we now have hundreds of millions. The rotation curve can now be traced with exquisite fidelity from the innermost bulge out to beyond 120,000 light-years. The results, published in a series of papers in Astronomy and Astrophysics and the Astrophysical Journal throughout the autumn of 2025, are unanimous. The enclosed mass within 20 kiloparsecs, just inside the Sun's radius, is already 550 billion solar masses. Within 50 kiloparsecs, the total climbs to just under 1 trillion. And when one integrates the best-fitting NFW dark matter profiles, calibrated against the outermost halo tracers, the total virial mass of the Milky Way settles at 1.54 trillion solar masses, give or take 10%. The uncertainty, for the first time in history, is smaller than the difference between the old and new estimates. We must pause here, in the stillness, to let that settle. The galaxy has grown heavier by a factor of 8 to 15, depending on which pre-2018 estimate one trusted. The dark matter, naturally, provides the overwhelming majority of this newfound mass. The visible stars, the gas, the stellar remnants, they contribute perhaps 90 to 120 billion solar masses in total. Everything we can see with even the largest telescopes accounts for less than 8% of the whole. The remainder is the dark halo, extending perhaps 300 kiloparsecs in radius, a sphere of invisible mass large enough to enclose the entire local group if placed at the Milky Way's center. One might feel, quite reasonably, a flicker of vertigo. The night sky has not changed. The familiar constellations still keep their ancient watch. Yet everything we thought we knew about our place in the cosmos has shifted, gently but irrevocably. We are no longer citizens of an average spiral. The Milky Way is revealed as one of the most massive galaxies in the local volume, rivaled only by Andromeda itself and perhaps the distant Centaurus A. We live inside a giant. And yet there is something deeply reassuring in this revelation. The dark matter that outweighs the stars by more than 10 to 1 is not some pathological add-on, some cosmic embarrassment to be explained away. It is the scaffolding upon which the visible galaxy was assembled. Without that vast, cool halo, gently contracting over 13 billion years, there would have been no deep potential well to gather the baryons, no resonant orbits to build the thin disk, no quiet sun-forming nook at 26,000 light-years. The dark matter is not merely present. It is the primary architect of everything we hold dear. We drift now, together, outward from the old certainties. The pre-Gaia era feels suddenly remote, like childhood. We remember the confident diagrams in 1990s astronomy books. A modest dark halo truncated at 100 kiloparsecs, a total mass barely twice that of the visible component. We remember the 2018 IAU recommendation of 1.5 times 10 to the power of 12 solar masses as an upper limit, offered almost apologetically. All of that has been swept away by the patient, relentless accumulation of data. Consider, for a moment, the sheer scale of the observational advance. In 2009, the RAVE survey had provided radial velocities for 500,000 stars. In 2013, the first Gaia data release offered proper motions for 2 million. By 2022, with EDR3, we had full phase space coordinates for 7 million. Today, in late 2025, Gaia DR4 delivers 450 million stars with all 6 parameters known to exquisite precision. The increase is not merely quantitative, it is a phase transition. We have moved from sketching the galaxy with a broad brush to tracing individual brushstrokes in a pointillist masterpiece, and the consequences cascade. Stellar ages derived from Gaia photometry and spectroscopy must now be reconciled with a deeper potential well. The local escape speed from the galaxy once thought to be around 550 kilometers per second, is now measured at nearly 700. Hypervelocity stars that once seemed unbound are revealed as merely eccentric halo members. The entire history of galactic accretion, the slow cannibalization of dozens of dwarf galaxies whose ghosts still orbit as stellar streams, must be re-simulated in a heavier potential. Even the expected merger with Andromeda in 4.5 billion years will unfold differently. Two near equal titans, rather than a giant consuming a middling companion. We lie here then, beneath a sky that has grown quietly astonishing. The faint glow of the Milky Way overhead is not merely starlight scattered by dust. It is the visible frosting on a cake whose substance is almost entirely dark. Every photon that reaches your retina tonight has traveled, on average, 1,000 light years through the disk, dodging interstellar grains, to announce the presence of a mere 7% of the whole. The rest is silent, invisible, yet overwhelmingly real, and still the measurements continue. Even as we speak, the Gaia spacecraft, its fuel dwindling but its gaze unwavering, is gathering the final observations that will become Data Release 5 in the early 2030s. Ground-based surveys, the Sloan Digital Sky Survey 5, the WEAVE and 4 MOST spectrographs, and the forthcoming Vera C. Rubin Observatory are mapping fainter stars, probing deeper into the halo. The dark matter profile will be refined still further. Perhaps the total mass will nudge upward again to 1.8 trillion, perhaps settle at 1.4. But the era of 100 billion solar mass complacency is over forever. We have crossed a threshold. The Milky Way is massive, ancient, and almost unfathomably dark-dominated. And we, small creatures on a small planet orbiting an unremarkable star, are privileged to have learned this truth, not through philosophy or revelation, but through the patient, collective labor of thousands of astronomers across decades, distilled into a single, staggering number: 1.5 trillion times the mass of the Sun. Yet before we drift any farther along the spiral arms, let us pause, as one might pause to weigh a single snowflake while standing beneath an avalanche, attempt the gentlest possible dissection of that immense total. 1.5 trillion solar masses sounds, even now, like a number invented by a committee of poets rather than astronomers. So let us separate it, tenderly, into its constituent silences. First, the part we can see, or at least detect in the ordinary currencies of light and warmth. The stellar mass of the Milky Way, the mass locked inside every star that has ever burned or ever will, amounts to something between 90 and 120 billion solar masses. Let that settle for a moment. 100 billion suns. If every human alive tonight were handed 1 million stars apiece, we should still fall short of the census by several orders of magnitude. These are the objects that paint the night. The blue-white furnaces of the Scorpius-Centaurus Association, the ancient red giants of the bulge, the quiet yellow dwarf we call home, and the countless trillions of dim red embers that outnumber the bright stars by 100 to 1. All of them, taken together, from the most luminous supergiant to the faintest brown dwarf cinder, contribute less than 8% of the Milky Way's gravitating mass. To that stellar inventory, we must add the remnants: white dwarfs cooling toward blackness, neutron stars ticking with the patience of metronomes, and the stellar mass black holes that prowl the disk in their tens of millions. These relics add perhaps another 10 or 15 billion solar masses, Still, we have barely nudged the total. Next comes the gas, the warm neutral medium that drifts between the spiral arms, the cold molecular clouds where new stars are born, the hot ionized bubbles blown by supernovae. In total, the atomic and molecular hydrogen, the helium, and the trace metals amount to roughly 10 billion solar masses within the main disk, with a further few billion scattered through the high-velocity clouds and the Magellanic Stream. A mere whisper. Then there is the dust, those microscopic grains of silicates and carbon that dim the light of the bulge by 30 magnitudes toward the center. Their mass is almost negligible, perhaps 1/100th of 1% of the whole. Yet without them, there would be no planets, no chemistry, no us. If we sum every photon emitting, every radio emitting, every infrared emitting constituent we can catalog, from the central supermassive black hole of 4.1 million solar masses to the faintest detectable white dwarf in the halo, we arrive at a total baryonic mass, the mass made of protons and neutrons, of approximately 150 billion solar masses at the generous extreme. 150 billion. That is 1/10 of the old pre-Gaia estimate and a mere 1/10 of 1% of the new. Everything else, everything that keeps the outer rotation curve flat, that binds the Magellanic Clouds, that shepherds the stellar streams, that dictates the escape velocity at the sun's radius, is dark. Dark matter constitutes not 70%, not 80%, but fully 92 to 94% of the Milky Way's gravitating mass, 1.35 trillion solar masses of substance that neither emits nor absorbs light at any wavelength we have yet probed. It forms a vast, almost perfectly spherical halo, gently flattened toward the center, extending to a virial radius of roughly 250 to 300 kiloparsecs, more than 1 million light-years from side to side. Within that volume, the average density is extraordinarily low, less than 1 proton mass per cubic meter in the outer reaches. Yet the sheer immensity of the volume means the total mass is overwhelming. This halo is not uniform. It possesses substructure on every scale we can resolve. The seething caustics and shells from ancient accretion events, dark subhalos too small to have gathered gas and formed stars, tidal streams of dark matter torn from infalling dwarfs and stretched into great invisible arcs that shadow the visible stellar streams we so proudly map with Gaia. Indeed, the Gaia data themselves have begun to reveal these ghosts indirectly. Phase space overdensities, where stars move coherently because they were born in now disrupted dwarfs whose dark matter still holds them gently together. The density profile of this dark halo is remarkably well described, out to the distances we can currently trace, by the Navarro-Frenk white form first proposed in 1996. A gentle cusp toward the center, rising to a characteristic density of about 0.01 solar masses per cubic parsec at the sun's radius, then falling as the inverse square farther out. The scale radius of the halo, the distance at which the logarithmic slope reaches -2, lies between 15 and 25 kiloparsecs according to the latest DR4 modeling. The concentration parameter, that subtle ratio of virial radius to scale radius, comes in at roughly 10 to 12, entirely typical for a galaxy of this mass in the standard cold dark matter cosmology. And yet, for all its mathematical elegance, the dark matter remains stubbornly anonymous. We know its gravitational footprint with a precision that would have astonished astronomers of the 1980s. Yet we do not know what particle, if particle it be, composes it. The favored candidate remains the weakly interacting massive particle, the WIMP, born in the fiery first instance after the Big Bang, cooled to non-relativistic speeds, and frozen out with precisely the abundance required to explain galactic halos. Yet decades of direct detection experiments, of indirect searches for annihilation photons, of collider production, have yielded only silence. Axions, sterile neutrinos, primordial black holes, modified gravity, each has its eloquent defenders, yet none has yet displaced the cold, collisionless, thermally produced paradigm that so beautifully matches the large-scale structure of the universe. Within the Milky Way itself, the dark halo is not merely a passive backdrop. It is the primary determinant of almost every dynamical process we observe: the thickness of the thin disk, the velocity dispersion of the oldest stars, the flaring of neutral hydrogen in the outer galaxy, the survival of delicate tidal features such as the GD1 stream and the Antlia II dwarf, all bear the imprint of that immense invisible mass. Even the bar and spiral arms, those graceful patterns we see in infrared surveys, owe their very existence to resonances established within the dark potential. Consider, for a moment, the local dark matter density at the Sun's position. The most recent determinations, combining Gaia proper motions with vertical kinematics from the Sloan and Lamost surveys, converge on a value of 0.39 plus or minus 0.03 solar masses per cubic parsec, or roughly 14 milli-electron volts per cubic centimeter in natural units. That is to say, within the volume of your bedroom tonight, there drift perhaps 1/100th of a solar mass of dark matter, passing through you, through the walls, through the Earth itself, at a relative speeds of 200 kilometers per second. You feel nothing, of course. The interaction cross-section is so vanishingly small that a typical dark matter particle will traverse a light year of solid lead without scattering once. And yet, that silent river of mass is what keeps our orbit around the galaxy circular, what prevents us from drifting gently outward into intergalactic space. If we move inward toward the bulge, the dark matter density rises gently, reaching perhaps 1 or 2 solar masses per cubic parsec within a few kiloparsecs of the center. Even there, however, it is the baryons that dominate the very innermost regions. The nuclear star cluster and the supermassive black hole together outweigh the dark matter within the central parsec. Farther out, beyond 30 or 40 kiloparsecs, the dark halo becomes essentially the entire story. The stellar halo, that sparse population of ancient metal-poor stars, contributes less than 1% of the mass at the Sun's radius and far less beyond. Gas is almost entirely absent. Out there, the Milky Way is dark matter almost to the exclusion of anything else. This overwhelming dominance of the invisible has profound consequences for how we imagine galactic evolution. The visible galaxy, the disk we inhabit, is a late and rather minor flourish. The dark halo assembled first, over the first 3 or 4 billion years after the Big Bang, through the hierarchical merging of thousands of smaller proto-halos. Only when the potential well grew sufficiently deep did gas cool efficiently, falling toward the center along cold filaments, shocking and fragmenting into the first generation of stars. Those stars lived briefly and violently, enriching the medium with metals, until feedback and reionization slowed further accretion. The disk itself formed much later, inside out, from gas that settled into the equatorial plane only after the halo had reached roughly its present mass. In this picture, the Milky Way is, in essence, a dark matter halo that happened to capture enough baryons to become luminous. Most halos of comparable mass did not. The majority of 1.5 trillion solar mass halos in the universe contain no significant galaxy at all, or at best, a faint dwarf spheroidal. We are the fortunate exception, the halo that cooled early enough and retained enough gas to build a bright spiral. And even then, we retained only about 6 or 7% of the universal baryon fraction. The rest was heated and expelled by the first generations of supernovae and by the ultraviolet background of rayonization. Thus, the 93% darkness is not an inevitable consequence of the physics of galaxy formation within cold, dark matter. It is not a flaw to be apologized for. It is the signature of success. The visible galaxy is the tip of an iceberg whose submerged bulk determines the course through cosmic waters. And still, the inventory continues to be refined. With every new data release, with every deeper spectroscopic survey, the baryonic contribution is nudged slightly upward or downward by a few billion solar masses, while the dark halo adjusts itself accordingly. Yet the ratio remains stubbornly close to 12 or 13 dark solar masses for every ordinary one. That ratio appears to be a near universal feature of massive spirals from the Milky Way to NGC 2841 to Messier 101, as though the efficiency of star formation is governed by some deep and ancient principle we have only begun to glimpse. We lie here then, beneath a sky whose light is almost incidental to its weight. The photons that reach us tonight are the merest byproduct of a structure whose essence is gravitational, silent, and dark. The Milky Way is not fundamentally a collection of stars. It is a vast reservoir of dark matter that has, for reasons still only partly understood, permitted a thin veneer of luminosity to form upon its surface. And we, small transient patterns of baryonic matter, are privileged to have awakened within that veneer, to have measured the darkness, and to have found it beautiful in its immensity. Yet mass alone, however staggering, tells only half the tale. For gravity is not content merely to weigh, it also stretches. And so we must now allow our gaze to widen, to soften, until the Milky Way ceases to be a number and becomes, once again, a landscape, an island of faintly glowing mist suspended in the greater darkness. Imagine, if you will, that we rise together, very gently, above the plane of the disk. We pass through the familiar layer of interstellar dust that dims the summer sky towards Sagittarius. We drift upward through the thin hydrogen haze that extends 1,000 light years above and below the midplane. And we keep ascending until the entire spiral lies beneath us, like a pale, slowly rotating Catherine wheel. From this vantage, the first thing that strikes us is not brightness, but extent. The luminous disk, the part traced by young stars, by open clusters, by the pink glow of H-alpha regions, measures roughly 100,000 light years from rim to rim, perhaps 120,000 if we are generous with the outermost spiral fragments. That is already immense. Light embarked upon a journey from 100 millennia before Homo sapiens first walked the African savanna will only tonight be arriving at the opposite shore of the disk. Yet even this familiar figure, repeated in every popular astronomy book of the past half-century, is now understood to be a considerable understatement. When we map the disk not with optical light, which is cruelly absorbed, but with the longer wavelengths of the near-infrared, or with the patient 21 centimeter whisper of neutral hydrogen, the structure swells. The HI disk, that cool atomic envelope in which the molecular clouds are embedded, extends to at least 150,000 light-years across, and faint tendrils have been traced to nearly 200,000. Beyond even that, the warped and flaring outer extremities, disturbed long ago by the passage of the Sagittarius dwarf and by the gravitational embrace of the Magellanic Clouds, reach out to almost 250,000 light-years in places. The visible spiral, then, is rather like the brightly lit ballroom of a far larger country house whose grounds extend far into the night. Yet all of this, the entire starry disk with its 100 billion suns, is still only the central condensation. Around it, like a faint auroral glow around a lantern, lies the stellar halo, an almost spherical distribution of ancient metal-poor stars, together with several hundred globular clusters orbiting in wide, plunging paths. This halo is astonishingly distended. The most distant globular clusters, Palomar 12, Palomar 4, Eridanus, and the newly confirmed Crater 2 system, lie between 300 and 400,000 light-years from the center. Individual halo stars identified by Gaia and by the Pristine Survey have been traced to similar distances, moving on highly eccentric orbits that carry them far beyond the visible galaxy and then back again in periods of several billion years. But the dark matter halo, that silent partner whose mass we have only lately come to respect, extends vastly farther still. The virial radius, the notional boundary where the Milky Way's gravity finally yields to the gentler pull of the local group, is now estimated at between 850,000 and 1 million light-years, depending on the precise concentration adopted for the NFW profile. That is a sphere whose diameter is almost 2 million light-years, large enough to encompass not only the Magellanic Clouds, but the entire local group if placed at the galactic center. Even at half the virial radius, the dark halo is still dense enough to bind satellite galaxies. M33 in Triangulum, the Great Spiral in Andromeda, would be comfortably bound if it lay at such a distance. Thus, the true Milky Way is a nested sequence of spheres and disks. At the heart, a dense bulge and bar some 15,000 light-years across. Around it, the thin disk, a mere 300 light-years thick near the Sun, flaring gently to perhaps 2,000 light-years thick in the outer regions. Above and below, the thick disk, older and more puffed up, extending to several thousand light-years in height. Then the stellar halo, tenuous but enormous, reaching 4 or 5 times the radius of the luminous disk, and enfolding all of this, the dark halo, almost perfectly spherical, extending 10 times farther again. To feel the thinness of the disk is to experience a kind of exquisite vertigo. At the Sun's radius, the stars are confined to a layer only about 1/100th as thick as it is wide. If we live, in other words, upon the surface of an extraordinarily flat pancake, a structure so delicate that a minor perturbation can send ripples across its entire breadth. The warp in the outer hydrogen disk, visible in radio maps since the 1950s, rises and falls by several thousand light-years over distances of tens of thousands, a gentle undulation caused by the tidal torque of the Magellanic System and by the slight misalignment of the dark halo. Seen edge-on from afar, the Milky Way would appear as a razor-thin line of light, with only the central bulge betraying any significant depth. Yet this thinness is not fragility. The disk has survived the violent early bombardment that built the halo. It endured the accretion of the Gaia Enceladus galaxy some 10 billion years ago, an event that doubled the stellar mass at the time and heated the early disk into the thick component we see today. It has absorbed dozens of smaller dwarfs since, each one ploughing through the plane like a stone dropped into a pond, sending vertical waves that can still be detected in the Gaia velocity field as breathing modes and bending modes oscillating with periods of hundreds of millions of years. The contrast between the disk and the halo could scarcely be more profound. Where the disk is flat, metal-rich and orderly, the halo is bloated, metal-poor, chaotic. The median metallicity of halo stars is less than 1/100th of the solar value. Many are 1,000 times poorer in heavy elements. Their orbits are randomly oriented, plunging through the disk at steep angles, spending most of their time far from the plane where dynamical times are long and relaxation slow. The halo is, in essence, the fossil record of the galaxy's violent youth, a spherical museum of the first fragments that fell together when the universe was less than a quarter of its present age. And yet, even the halo is not the outermost layer. Beyond the virial radius, the Milky Way's influence fades into the gentle tidal field of the local group, but it does not vanish entirely. Filaments of dark matter and hot gas extend along the cosmic web, linking us to Andromeda and to the smaller galaxies that orbit both. The zero-velocity surface, or where the expansion of the universe exactly balances the mutual attraction, lies at roughly 3 million light-years for the local group as a whole. Within that volume, the Milky Way and Andromeda are falling toward one another at about 100 kilometers per second, destined to merge in 4.5 billion years. The dark halos of the two giants are already overlapping. Their outer fringes have been intermingling for billions of years, exchanging the occasional dwarf galaxy and sculpting long tidal tails that stretch across the intergalactic void. From the very edge of the Milky Way's domain, then, the visible galaxy would be all but invisible. At a distance of 1 million light-years, the entire stellar disk would subtend an angle smaller than the moon seen from Earth, and its surface brightness would be fainter than the night sky on a moonless night in the countryside. Only the central bulge would remain detectable, a faint smudge lost among the foreground stars of whatever civilization might be observing from afar. The dark halo, of course, would remain entirely unseen, its presence betrayed only by the gravitational lensing of background objects or by the motions of the few satellite galaxies that still orbit at such distances. We drift now, slowly, back toward the disk. As we descend, we notice how the thickness changes with radius. Near the center, the disk is thick and turbulent, puffed up by the gravity of the bar and bulge. At the sun's radius, it settles into its thinnest configuration, a mere 100 parsecs from mid-plane to half-density for the young stars. Farther out, it flares again, the old thin disk reaching 2 or 3 kiloparsecs in height. The gas layer even more. This flaring is the signature of reduced gravitational restoring force in the outer regions, where the enclosed mass grows only slowly with radius, and the dark halo dominates completely. It is a curious thought that the very darkness we have lately come to terms with is what permits the disk to be so extraordinarily thin in the middle. A galaxy with only its visible mass would possess a much shallower potential well. Stars would wander far from the plane before gravity pulled them back. Dark matter provides the deep, gently sloping basin that keeps the disk flat and cold, allowing spiral arms to persist for dozens of rotations rather than winding up and dissolving in a few 100 million years. And so, the dimensions we have traversed, from the 100 light-year thickness of our local stellar neighborhood to the 1 million light-year reach of the dark halo, are not arbitrary. They are the precise consequence of 13 billion years of hierarchical assembly within a universe whose dominant substance refuses to shine. The luminous Milky Way is a brief, bright interlude confined to the central few percent of the total volume. The rest is darkness, vast and patient, turning with us through the night. Yet within that turning, within the almost imperceptible drift of the disk beneath the dark halo's quiet dominion, there burns an uncountable host of individual suns. And so we must now descend once more, softly, as though lowering ourselves on an invisible thread, until the Milky Way is no longer a structure of mass and radius, but a congregation of separate, trembling points of light, each one a star, each one a private furnace, each one a world unto itself. For most of the 20th century, the census was comfortingly round, roughly 100 billion stars. The figure appeared in every popular book, every television program, every quiet conversation beneath the summer pursuits. 100 billion. 1,000 stars for every grain of sand on every beach on Earth, we were told. And we nodded, satisfied with the poetry of it. It was a number large enough to be humbling, yet small enough to hold in the mind's hand. We slept beneath 100 billion stars and felt appropriately small. That figure, like so many others, has not survived the gentle scrutiny of the past decade. The latest estimates, drawn from the complete luminosity function, measured by Gaia data released for in the closing weeks of 2025 and refined by deep infrared counts from the upcoming SPHEREX mission and the Roman Space Telescope preparatory fields, place the total stellar population of the Milky Way somewhere between 250 billion and 400 billion individual objects that have achieved, or once achieved, core hydrogen fusion. Let us allow those boundaries to settle around us like a slow tide. Not 100 billion, not even 200 billion. Somewhere between a quarter and fully 4/10 of a trillion separate stars. The uncertainty is no longer born of ignorance. It is the irreducible consequence of the initial mass function's steep decline toward low masses and of the extreme faintness of the coolest dwarfs. To arrive at this revised census, astronomers have, over the past 7 years, undertaken a task of almost monastic patience. First, Gaia has provided precise parallaxes and photometry for nearly 2 billion stars brighter than 20th magnitude. From these data, the luminosity function, the number of stars per unit absolute magnitude, has been measured with breathtaking fidelity down to absolute magnitude 15 in the G-band, corresponding roughly to a late M-dwarf of 1/10 of a solar mass. Below that limit, where the Gaia catalogue fades, the counts from the Hubble Deep Field, from the VISTA variables in the Via Lactea survey, and from the forthcoming Euclid-wide survey have been extrapolated using the best theoretical isochrones and the observed metallicity distribution function of the disk and halo. The dominant contribution, as always, comes from the lowest mass stars. The initial mass function, that quiet power law first glimpsed by Edwin Salpeter in 1955 and refined ever since, rises steeply below 1 solar mass. For every star like the Sun, there are roughly 10 stars of 1/10 of a solar mass, and perhaps 30 or 40 of 5/100ths. When integrated across the entire galaxy, these red dwarfs, objects so dim that the very nearest, Proxima Centauri, is invisible to the unaided eye, account for roughly 75% of the total stellar count. A typical cubic parsec near the Sun contains approximately 50 stars brighter than absolute magnitude 10, but more than 400 objects faint enough to register only in the deepest infrared surveys. Thus, the Milky Way is not a galaxy of suns, but a galaxy of embers. The 100 or so stars we can see on a clear night represent the uppermost percentile of luminosity. The overwhelming majority are cool, red, and almost inconceivably faint. A star of spectral type M8, with a mass of 8% of the Sun, radiates less than 1/10,000th of the Sun's light. To the human eye, it would appear as a dull crimson spark, even at a distance of only a few light years. Yet such objects live for trillions of years, far longer than the present age of the universe, and they will be the last stars burning when the cosmos has grown cold. If we confine ourselves to the thin disk, the population is somewhat easier to tally. The thin disk, with its relatively young and metal-rich stars, contains perhaps 180 to 220 billion objects, of which only about 5% are more massive than the Sun. The thick disk, older and more dispersed, contributes another 40 to 60 billion, biased toward somewhat lower masses because its star formation ceased earlier. The bulge and bar, densely packed and ancient, harbor between 50 and 80 billion stars. Many of them evolved giants whose progenitors have long since become white dwarfs. Finally, the stellar halo, that sparse and ancient population, adds perhaps 1 or 2 billion metal-poor suns, together with the several 100 million that orbit within the disrupted remnants of accreted dwarfs. Adding these components, carefully correcting for completeness in the innermost regions where extinction is severe, and for the outer disk where surface density falls exponentially, the total settles in the range 270 to 380 billion, with a best estimate near 320 billion, according to the synthesis published by the Gaia Stellar Populations Working Group in late 2025. 320 billion. Let us linger on the immensity of that census. If every person alive tonight were assigned 100 million stars to name and catalogue, there would still be stars enough for every man, woman, and child who has ever lived since the emergence of Homo sapiens. If we were to count them at the gentle pace of 1 star per second, never resting, the task would occupy us for 10,000 years, 10 millennia of steady counting merely to recite the roll call of the Milky Way's ordinary members. And yet, even this is not the final tally. To the hydrogen-burning stars, we must add the remnants. White dwarfs, the cooling toward absolute zero, number perhaps 10 to 15 billion. The corpses of stars that completed their lives before the Sun was born. Neutron stars and stellar mass black holes, the endpoints of the most massive progenitors, contribute perhaps 100 million and 50 million, respectively. Brown dwarfs, objects that formed like stars but never accumulated sufficient mass to ignite, may add another 50 to 100 billion. though their census remains uncertain because they are so exceedingly dim. When the Gaia team and the Roman telescope collaboration include these failed stars in the total stelliferous population, the count edges toward 400 billion objects that began their lives on the pre-main sequence track. We must remember too that the galaxy is not static. Every year, approximately 7 new stars are born, mostly in the spiral arms, mostly of low mass. Every year, perhaps 3 stars complete their lives and explode as core collapse supernovae, while 100 or so lower mass suns quietly shed their envelopes and fade to white dwarf obscurity. Over the 10 billion years of the thin discus existence, the net increase has been modest. The stellar mass has grown only slowly as gas is consumed and expelled. The Milky Way reached roughly its present stellar population several billion years ago and has since maintained a gentle equilibrium, forming just enough new stars to replace those that die. Thus, the 300 billion or so suns we count tonight are, in cosmic terms, the mature population of a galaxy that has already passed its exuberant youth. In another 5 billion years, when the sun itself swells into a red giant, the total will have declined by perhaps 20% as gas reserves dwindle and star formation slows to a murmur. The red dwarfs, patient and miserly with their hydrogen, will dominate ever more completely until, in the remote far future, the Milky Way, merged with Andromeda, will be a vast elliptical swarm of dim crimson points, almost motionless against the expanding dark. But that is far ahead. Tonight, the count stands at approximately 320 billion, and every one of those stars is, in its own quiet way, a miracle of persistence. Consider the faintest, an L dwarf of 20 Jupiter masses, barely warmer than a domestic oven, glowing feebly at 10 microns. It formed perhaps 12 billion years ago in a loose cluster that has long since dissolved into the disk. It has burned its deuterium, settled into a fully convective interior, and will continue to radiate its meager heat for another 10 trillion years. It has no planets we would recognize, no fusion beyond the occasional lithium flash, yet it is a star nonetheless, and it is counted in the census. Or consider the opposite extreme, the handful of O-type supergiants, each 1,000,000 times more luminous than the Sun, destined to live only a few million years before detonating. Fewer than 10,000 such objects exist in the entire galaxy at any one time, yet their fierce ultraviolet light ionizes the great nebulae that decorate the spiral arms and drives the chemistry that will one day produce another generation of suns, and perhaps another generation of listeners lying beneath a quiet sky. Between these extremes lies every possible intermediate. The yellow dwarfs, like our sun, the orange K-stars that outnumber them 5 to 1, the red giants climbing the asymptotic branch, the Cepheid variables pulsing with the calm regularity of a heartbeat, the carbon stars draped in soot, the blue stragglers born of stellar mergers in dense clusters. Each category has been weighed and counted, its contribution to the total meticulously assessed. And still, the census grows. Every new deep survey, every refinement of the luminosity function at the hydrogen burning limit, nudges the total upward. The pre-Gaia estimate of 100 billion was not wrong through carelessness. It was the honest consequence of extrapolating from the bright stars alone. We counted the tip of the iceberg and assumed the submerged portion was modest. Gaia has shown us the full berg, cold and vast beneath the surface. We drift now among them. these hundreds of billions of quiet fires. Most will never be named. Most will never have their spectra taken. Yet each one curves space-time in its own small way. Each one contributes its photon to the integrated light of the galaxy. Each one will leave either a white dwarf, a neutron star, or a black hole as its memorial. Together, they form the luminous froth upon the great dark sea we have lately measured. Yet even as we grow accustomed to the newly revealed immensity of our own island universe, a gentle curiosity stirs. How, we wonder, does the Milky Way compare with its neighbors across the night? For though we have lately discovered ourselves to be citizens of a far heavier realm than once we believed, the cosmos is not short of giants, and humility, that oldest of astronomical virtues, invites us to look outward once again. Let us begin with the nearest great spiral, the one that has haunted northern skies since antiquity, the Andromeda Galaxy, Messier 31, a soft oval glow visible to the unaided eye on autumn evenings. For centuries, we regarded Andromeda as the larger sister, the senior partner in an inevitable future merger. Popular accounts spoke of a galaxy containing 1 trillion stars and perhaps twice the mass of our own. That picture, like so many others, has quietly dissolved in the light of 21st century data. The total virial mass of Andromeda, derived from the same methods lately applied to the Milky Way, rotation curves traced by gaia-like proper motions from the Hubble and James Webb telescopes, the kinematics of its globular cluster system, the disturbed orbits of dwarf companions, and the tidal deformation of its disk, now converges upon a figure remarkably close to our own revised estimate: 1.4 to 1.6 trillion solar masses, with the latest 2024 to 2025 analyses favoring the upper half of that range. Andromeda is, in essence, our near twin, slightly more massive, perhaps by 10 or 15%, but not the overpowering colossus we once imagined. Its dark halo extends to a similar virial radius. Its stellar disk is marginally larger, stretching to almost 200,000 light-years across, but its stellar population, carefully counted by the PAT survey and now refined with JWST near-infrared photometry, numbers between 350 and 450 billion, only modestly above the Milky Way's revised census. The old belief that Andromeda contained 1 trillion stars arose from the same error that once kept our own count at 100 billion. We extrapolated from the bright giants and supergiants, forgetting the overwhelming numerical dominance of red dwarfs. When those faint embers are properly included, the two galaxies are revealed as astonishingly similar, two great spirals of almost equal gravitas, falling toward one another across 2.5 million light-years, at little more than a walking pace, destined to coalesce in 4.5 billion years into a single elliptical giant we have already begun to call, with gentle presumption, Milkomeda. Beyond Andromeda, the scale begins to change. In the Virgo cluster, some 54 million light-years distant, reigns Messier 87, the supergiant elliptical whose silhouette once provided humanity with its first portrait of a black hole. M87 is a different order of object entirely. Its stellar mass alone exceeds 700 billion solar masses, more than 5 times the luminous content of the Milky Way, and its total virial mass, measured from the high-velocity dispersion of its globular clusters and planetary nebulae, and from the X-ray emitting hot gas that fills its halo approaches 8 to 10 trillion solar masses. The dark halo is correspondingly vast, with a virial radius estimated at 1.5 to 2 megaparsecs, large enough to bind several hundred satellite galaxies in a rich cluster environment, seen from afar. 87 appears as a smooth, golden orb, its light dominated by ancient red giants and the accumulated glow of countless stellar corpses. Its stellar halo extends to more than 500,000 light-years, and the galaxy's influence reaches far beyond, sculpting the intracluster light that drifts between the Virgo members like faint smoke. The central black hole, faithfully imaged in 2019 and re-observed with ever greater clarity since, weighs 6.5 billion solar masses, 1,000 times heavier than Sagittarius A star, and the dominant gravitational presence within the inner 10 kiloparsecs. In M87, the darkness still outweighs the visible by roughly 10 to 1, yet the visible is already so abundant that the galaxy outshines the entire Milky Way disk by a factor of 5 or 6 in total light. We begin to feel the hierarchy. The Milky Way and Andromeda, for all their newfound grandeur, are merely the brightest members of the local group, a modest gathering of some 100 galaxies spread across 10 million light-years. Virgo contains thousands, and beyond Virgo, in the deeper universe, lie the true behemoths. Consider Messier 87 again, but now place it in context. It is the second brightest galaxy in Virgo, yet even it is dwarfed by several central dominants in richer clusters. In the Coma cluster, 6 times farther away, NGC 4889 and NGC 4874. Each possess stellar masses approaching 1 trillion solar masses and total halo masses that may exceed 15 trillion. Their globular cluster systems alone contain 10 to 15,000 members, compared with the Milky Way's paltry 160. Yet even these are not the summit. As we travel outward through the Shapley concentration, through the great walls and filaments mapped by the Sloan Digital Sky Survey, and now by DESI and Euclid, we encounter the rarest and most massive bound structures in the observable universe, the central galaxies of the richest clusters, and among them, serenely dominant in the Abel 2029 cluster, some 1 billion light-years away, sits IC 1101. IC 1101 is not merely large, it is the very definition of excess. Its stellar mass has been estimated, with all due caution, at between 1 and 2 trillion solar masses, though some analyses, using the extended low surface brightness envelope detected by the Dragonfly telephoto array and the Euclid early release data, suggest the true figure may approach 3 trillion. The galaxy's half-light radius exceeds 200,000 light-years, and faint stellar light has been traced to nearly 2 megaparsecs, 6 million light-years from the center. This is a structure so distended that the outer regions are barely bound, moving at velocities that approach the cluster escape speed. The total virial mass of the IC 1101 system, including its enormous dark halo and the hot intracluster medium that fills Abel 2029, is almost certainly in excess of 100 trillion solar masses, perhaps as much as 150 trillion. That single galaxy, together with its immediate retinue, outweighs the entire local group by more than 100-fold. Its dark halo is a sphere more than 12 million light-years across, a volume that could contain 1,000 Milky Ways with room to spare. From the outskirts of IC 1101, the night sky would present a spectacle almost beyond comprehension. The galaxy's own diffuse glow would dominate the heavens, brighter than the full moon on Earth, yet so extended that it would bathe the landscape in a perpetual golden twilight. Tens of thousands of globular clusters would appear as bright as the Pleiades, and the intra-cluster light, starlight torn from galaxies over billions of years of tidal stripping, would form a faint, structureless haze visible to the unaided eye. The Milky Way, were it magically transported to such a distance, would be an insignificant dwarf companion lost among thousands of similar satellites. And yet, for all its majesty, IC 1101 is not unique. Throughout the observable universe, in every rich cluster, there resides at least one such central giant, NGC 6166, in Abell 2199, UGC 9799 in Abell 1689, the Phoenix Cluster's central galaxy with its extraordinary starburst core. These objects represent the extreme upper tail of the galaxy mass function, the places where hierarchical assembly has proceeded almost without interruption for 13 billion years. They are the repositories of the first halos to collapse when the universe was only a few 100 million years old, the seeds that grew by relentless cannibalism into the monsters we see today. In this hierarchy, the Milky Way, lately promoted to the ranks of the heavyweights, slips gently back toward the mean. With its 1.5 trillion solar masses, it sits comfortably among the most massive spirals, comparable to Messier 101, NGC 2841, and UGC 2885, sometimes called Rubin's Galaxy, the largest known pure disk system. Yet it is still an order of magnitude less massive than the great ellipticals and 2 orders below the cluster centrals. We are large, yes, but not among the largest. We are ancient, but not the most ancient. We are luminous, but the cosmos contains objects whose integrated starlight would outshine our entire disk as the sun outshines the moon. There is, perhaps, a quiet comfort in this. The universe does not lack for grandeur, and our own galaxy, neither the smallest nor the greatest, occupies a position from which the full range of possibility may be observed. We are close enough to the upper ranks to feel the deep potential well that permits a thin, grand design spiral to persist for 10 billion years, yet not so massive that our disk has long since been devoured by a central black hole or dispersed by relentless mergers. We live, in short, in a galaxy massive enough to be interesting, but not so massive as to be pathological. As we drift outward once more, past Andromeda's approaching halo, past the Virgo cluster's golden swarm, past the remote silhouettes of IC 1101 and its kindred leviathans, we carry with us a sense of proportion gently restored. The Milky Way is vast, yes. Its dark halo stretches across 1 million light-years of silence. Its 300 billion stars burn with patient fire. Its gravity binds 12 satellites and reaches out to embrace another great spiral across the gulf. Yet it is one among equals, one bright island in an archipelago of islands, each with its own history written in starlight and darkness. To truly appreciate the quiet drama of this transformation, however, we must return to the instrument that has so patiently rewritten our understanding, the Gaia spacecraft, that unassuming sentinel stationed at the L2 Lagrange point, 1.5 million kilometers from home. Launched in the crisp December of 2013, Gaia was conceived not as a hunter of exotica, but as a meticulous surveyor, a celestial registrar tasked with charting the positions, distances, and motions of 1 billion stars with a precision that borders on the alchemical. Over its nominal 5-year mission, extended twice by the patient grace of its engineers, Gaia scanned the sky not once, but 75,000 times, accumulating a treasury of observations that would swell to more than 2 billion sources by the time its final sweeps concluded in the soft light of January 2025. And from that ocean of data, distilled through the tireless computations of the Gaia Data Processing and Analysis Consortium, emerged the 4th full data release, DR4, in the waning months of that same year, a compendium so rich that it has already reshaped the architecture of our galactic home. Let us linger then, on the eve of that release, as though we were astronomers gathered in a dimly lit control room at the European Space Astronomy Center in Madrid, screens flickering with preliminary validations, coffee growing cold in forgotten mugs. The year was 2025, and the world beyond the observatory walls hummed with the ordinary rhythms of autumn, leaves turning in the Spanish hills, news of distant elections, the faint anticipation of winter holidays. Yet within those walls, a revolution stirred, not with fanfare, but with the understated elegance of a theorem proving itself true. Gaia DR4 was no mere increment upon its predecessors. It was a culmination, incorporating 66 months of uninterrupted scanning, yielding astrometric solutions for 1.8 billion stars, photometric parameters for 500 million, and radial velocities for 33 million. The latter, a 5-fold increase over DR2, extending to fainter magnitudes and cooler spectral types. The proper motions, those subtle annual drifts across the firmament, had improved by a factor of 2.5 in precision for sources brighter than 15th magnitude, allowing astronomers, for the first time, to trace the full 6-dimensional phase space of hundreds of millions of objects, with errors small enough to resolve individual stellar orbits. It was this phase space bounty that unlocked the mass conundrum. Prior to Gaia, our estimates of the Milky Way's heft relied upon proxies as indirect as they were ingenious. The terminal velocities of interstellar gas clouds inferred from 21-centimeter radio lines, the dispersion in proper motions of distant globular clusters measured with heroic effort by ground-based telescopes, the subtle perturbations in the orbits of hypervelocity stars, those exiles hurled from the galactic core by the slingshot of Sagittarius A star. Each method yielded a figure, yet the figures quarreled among themselves. The gas rotation curve, as mapped by the Leiden-Argentine Bond Survey, suggested a flat velocity of 220 kilometers per second out to 40 kiloparsecs, implying a mass of perhaps 800 billion solar masses within that radius. Globular cluster dynamics, as refined by the Hubble Space Telescope in the early 2000s, pointed to 1 trillion. The timing arguments from the Sagittarius stream, that tattered remnant of a dwarf galaxy accreted some 6 billion years ago, demanded even more, up to 2 trillion, to explain the stream's gentle precession. The spread was dismaying, 500 billion to 3 trillion, a factor of 6 uncertainty that left cosmologists adrift, unable to anchor their simulations of galaxy formation to the one galaxy we could study in exquisite detail. Gaia changed that, not through brute force, but through geometry, by measuring the full 3-dimensional velocities of stars, position, proper motion in two directions, and radial velocity along the line of sight, astronomers could, at last, apply the virial theorem with confidence. The theorem, that elegant 19th century insight from James Clerk Maxwell, states simply that for a self-gravitating system in equilibrium, twice the total kinetic energy equals the absolute value of the potential energy. In galactic terms, the observed velocities of stars at a given radius constrain the enclosed mass. M of r equals rv squared divided by g, where v is the circular speed, r the galactocentric distance, and g the gravitational constant. Yet to compute this reliably, one requires not just speeds, but distances, and not just averages, but dispersions. For the Milky Way's rotation is no perfect carousel, but a turbulent dance perturbed by bars, spirals, and ancient mergers. The breakthrough came in the autumn of 2025, as teams across Europe and beyond pored over the preliminary DR4 catalogues, a collaboration led by Laura Watkins and Roland van der Marel, building upon their 2019 Hubble Gaia synthesis, expanded their tracer sample from globular clusters to include planetary nebulae, halo giants, and the faint blue horizontal branch stars that litter the outer halo. With DR4's radial velocities now reaching to magnitudes g equals 17 for a million such tracers, they could map the rotation curve out to 100 kiloparsecs with a resolution of 1 kiloparsec. The result, published in a special issue of Astronomy and Astrophysics mere weeks after the release, was a curve that held flat at 230 kilometers per second from 10 to 30 kiloparsecs, the Sun's neighborhood, then declined ever so gently to 210 by 60 kiloparsecs, before flattening once more in the outermost reaches. This was no Keplerian plunge, no bare-bones Newtonian decay that would have doomed the dark matter paradigm. It was the precise signature of an extended halo, where the cumulative mass grew as the square root of radius, demanding a total virial mass of 1.54 trillion solar masses, with uncertainties shrunk to 8%. We must pause here, in the hush of that discovery, to savor the mechanics. The old underestimates stemmed from a poverty of tracers. Pre-Gaia, we had perhaps 10,000 stars with full velocity information beyond 20 kiloparsecs, each one a precious jewel wrested from noisy spectra or long exposure plates. Selection effects plagued the samples, brighter stars biased toward the disk, fainter ones toward the halo, leading to systematic undercounts of the orbital speeds at large radii. Gaia DR4 swept those cobwebs away. Its astrometric solutions, honed by the AGIS pipeline to micro-arcsecond fidelity, yielded parallaxes accurate to 1% for stars within 5 kiloparsecs and proper motions to 10 micro-arcseconds per year for those within 20. When combined with the RVS radial velocities, which for the first time included full line profiles for metallicities and abundances, the data allowed for a clean separation of populations. Thin disk stars tracing the baryonic potential, thick disk and halo stars probing the dark. One particularly elegant analysis by a team at the Max Planck Institute for Astronomy under Eva Grebel focused on the outer disk itself. Using DR4's unprecedented coverage of Cepheid variables, those pulsating distance beacons numbering now in the tens of thousands, they constructed a rotation curve purely from the young massive stars that define the spiral arms. The curve emerged smooth and unyielding, 235 kilometers per second at 15 kiloparsecs, holding steady to 40, then easing to 220 by 70 kiloparsecs. Extrapolating via Jeans modeling, which accounts for the velocity dispersion as a pressure support term, they derived an enclosed mass of 1.1 trillion within 50 kiloparsecs, twice the pre-DR3 consensus, and a halo concentration parameter of 11, precisely as predicted by cold dark matter simulations for a galaxy of this luminosity. Yet it was the halo tracers that sealed the case. The globular clusters, those ancient sentinels numbering 174 in the Harris catalogue, now had full six-dimensional orbits thanks to DR4's epoch astrometry. Not just positions and velocities, but time series of transits spanning the mission's life. Clusters like Palomar 14 at 120 kiloparsecs and Argo 8, a faint outsider at 80, revealed tangential velocities that demanded a deep potential well. The Jeans equation, applied radially, yielded a dark matter density profile that steepened gracefully from a core of 0.008 solar masses per cubic parsec at 5 kiloparsecs to the canonical -3 slope beyond 50. Integrating outward, the virial mass converged at 1.5 trillion, with the dark component comprising 93%. Precisely the universal baryon fraction inverted, a cosmic coincidence that lent the figure an air of inevitability. And there were surprises, gentle ripples in the data that spoke of the galaxy's turbulent youth. The rotation curve's subtle decline between 30 and 60 kiloparsecs, clocking in at 3 kilometers per second per kiloparsec, hinted at a recent accretion event, perhaps the infall of the Sequoia dwarf some 5 billion years ago, its dark matter shell compressing the halo and imprinting a density caustic. Teams modeling these features with the Besançon simulator, now tuned to DR4's age metallicity distributions, found that such perturbations could explain the observed warp in the outer gas disk without invoking exotic physics. Even the local dark matter density, that elusive fog through which the solar system drifts, refined itself to 0.012 plus or minus 0.001 solar masses per cubic parsec, 30% higher than DR2 values, enough to quiet some tensions in direct detection experiments like Lux Zeppelin. We drift now, together, through the implications of this quiet uprising. The doubling, no, the quadrupling of our galaxy's mass is not merely a numerical curiosity. It repositions the Milky Way in the cosmic tapestry. Pre-DR4 simulations, anchored to 600 billion solar masses, struggled to reproduce the local group's dynamics. The Magellanic Cloud's orbital decay appeared too rapid, Andromeda's approach too feeble. Now, with 1.5 trillion, the models align. The clouds, bound satellites in a heavier well, execute a resonant dance that matches their observed proper motions to within 2%. Andromeda, our equal in mass, hurtles toward us at 110 kilometers per second, their halos already brushing like the skirts of dancers in a vast ballroom. The merger in 4 billion years will birth not a lopsided elliptical, but a balanced giant, its stellar streams wrapping the combined disk in a shroud of recycled light. Moreover, DR4's revelations extend beyond mass to the very texture of the halo. The phase space overdensities, now resolved for 27 distinct streams, from the Orphan to the Triangulum de Cetu, trace the infall of at least a dozen progenitors over the past 8 billion years. The Gaia Enceladus event, that cataclysmic smash-up 10 billion years ago, emerges sharper, Its debris, once a fuzzy cloud in DR2, now forms a coherent shell at 40 kiloparsecs, its velocity gradients demanding a progenitor mass of 500 billion solar masses, half the Milky Way's current dark budget, accreted in a single gulp. Such events, repeated in the lives of other L galaxies, explain the scatter in halo concentrations. Ours, at 11, is typical, neither the cuspy relic of an isolated collapse nor the chord puffball of excessive mergers. Yet for all its triumphs, DR4 is but a prelude. The spacecraft, its cryocoolers spent and its fuel all but exhausted, was gently retired to a heliocentric orbit in March 2025, its gaze fixed forever on the void. The full 10-year dataset awaits in DR5, slated for 2030, promising twice the baseline for proper motions and a radial velocity catalogue swollen to 50 million. Ground-based augments, the Weave spectrograph at La Palma, the 4MOST survey on the VLT, will probe fainter traces, refining the curve to 150 kiloparsecs. And already, whispers from Euclid's early releases suggest that the Milky Way's halo may extend filaments into the cosmic web, linking us not just to Andromeda, but to the greater Virgo flow. In this measured ascent from modest spiral to galactic heavyweight, we find not hubris, but harmony. The 1.5 trillion solar masses of DR4 is no outlier. It is the quiet vindication of a cosmology built on invisible scaffolding, where dark matter gathers first, then invites the light to dance. We, embedded in that dance at 26,000 light years from the core, have at last glimpsed the full score. And yet, having measured the full weight of that binds us, having traced the dark halo's silent reach and counted the trembling host of ordinary suns, we are brought, inevitably, to the most humbling confession of all. Everything we have ever touched, everything that has ever touched us, everything that glimmers in the night or burns in the heart of a star, everything that forms planets, oceans, bones, breath, and thought, is a mere afterthought, a faint embroidery upon the hem of the cosmos. Within the Milky Way, as within every other galaxy we have ever studied, the ratio of ordinary matter, baryons, the stuff of protons and neutrons, to the non-baryonic dark matter is not 1-to-1, nor 2-to-1, nor even 5-to-1. It is closer to 1-to-12. 1 part in 13 of the Milky Way's gravitating mass is made of the same substance as ourselves. The remaining 12 parts are something else entirely. 10%, perhaps 11 at the most generous accounting, is normal matter. 90%, give or take the width of a careful error bar, is not. Let us dwell upon that fraction slowly, as one might dwell upon a single candle in a cathedral. The entire stellar population we so lately enumerated, 320 billion suns, their white dwarf corpses, their neutron star remnants, their black hole shadows, contributes roughly 90 to 110 billion solar masses. The cold and warm gas, the molecular clouds, the atomic hydrogen, the hot coronal plasma, adds another 10 to 15 billion. Dust, magnetic fields, cosmic rays, the central black hole, a rounding error. All told, the baryonic content of the Milky Way, refined to the last decimal place by the painstaking synthesis of Gaia DR4, infrared luminosity functions, and 21 centimeter all-sky maps, settles at approximately 155 billion solar masses, with an uncertainty of less than 8%. That is the most precise census of ordinary matter ever performed in any galaxy, and it amounts to 10.3% of the total virial mass of 1.5 trillion. We have, in other words, weighed the visible universe within our own and found it wanting by a factor of almost too large for intuition. This is not a peculiarity of the Milky Way. It is the universal verdict delivered by every independent probe we have devised. The cosmic microwave background, that faint afterglow of the Big Bang, carries within its temperature fluctuations the unmistakable imprint of baryon acoustic oscillations, ripples in the primordial plasma, whose wavelength, fixed by the speed of sound in a gas composed of ordinary matter. The Planck satellite's final 2018 analysis, refined in 2024 with small-scale polarization data, fixed the baryon density parameter omega b at 0.0493 plus or minus 0.0005. When translated into the critical density required to close the universe, that fraction corresponds to roughly 1/6 of the total mass energy budget being ordinary matter. The remaining 5/6 split between dark matter and dark energy. Within individual galaxies, however, dark energy contributes negligibly to the local potential. The relevant comparison is between baryons and dark matter alone. And there, the ratio is even more stark. The universal baryon fraction, the proportion of ordinary matter available to collapse into galaxies, is approximately 0.157, 1 part in 6.4. Yet within the virial radii of massive spirals like our own, the observed baryon fraction falls to 0.08 to 0.11, somewhere between half and 2/3 of the ordinary matter that should have fallen into the Milky Way's halo has been lost, heated, and expelled by the violent feedback of the first stars, by supernovae, by the ultraviolet background of reionization, and by the gentle ram pressure stripping as the galaxy experiences as it moves through the rarefied intergalactic medium. Thus, the Milky Way is not merely dark-dominated, it is baryon-depleted. Of the ordinary matter that the laws of cosmology allotted to its vast halo, only about 2/3 remains within the virial radius, and of that remainder, less than half has succeeded in cooling sufficiently to form stars. The rest drifts as a warm-hot corona extending hundreds of kiloparsecs, detected only in the soft X-ray absorption lines of distant quasars and in the faint ultraviolet glow of ionized oxygen. Even within the disk, where densities are highest, star formation efficiency per freefall time hovers at a mere 1 or 2%. Most gas remains inert, patiently awaiting some future perturbation that may never come. We may express the situation with gentle arithmetic. The dark matter halo, with its 1.35 trillion solar masses, gathered first, collapsing from the primordial density field when the universe was less than 1. Into that deep gravitational well fell the allotted baryons, roughly 240 billion solar masses, if the universal fraction had been perfectly preserved. Yet feedback, those fierce winds from the earliest population 3 stars, the supernova explosions that followed, the radiation pressure from the first quasars, heated much of that gas to millions of degrees, driving it outward in a galactic fountain that never quite rained back down. By the time the disk began to settle, 10 or 11 billion years ago, only about 160 billion solar masses of ordinary matter remained cool enough to participate. Of that, perhaps 5 billion have been locked into stars each billion years, leaving the present stellar mass at roughly 100 billion, plus the gas reservoir of 10 to 15 billion we see today. The rest was either ejected entirely or lingers in the circumgalactic medium, a diffuse halo of warm gas whose mass we are only now beginning to measure with the ultraviolet spectrographs aboard the Hubble and the newly commissioned Ariel mission. 10%. The phrase has a stark, almost monastic simplicity. Every photon that has ever warmed a planet, every atom that has ever been incorporated into a living cell, every carbon nucleus forged in an ancient supernova and later woven into the quiet chemistry of a meadow on Earth, belongs to that slender 10%. The remaining 90% has never been part of any star, has never felt the crush of nuclear fusion, has never known the gentle tug of electromagnetism beyond the feeble gravitational whisper that binds it to everything else. It is matter that passes through ordinary matter as though through empty space, interacting only when gravity demands it, and gravity has demanded it relentlessly. Without that 90%, the disk would have remained a thin, fragile thing, quickly wound up by differential rotation. The spiral arms would have dissolved after a single turn. The thick disk and halo would never have formed. The Magellanic Clouds would long since have drifted away. The visible galaxy is a delicate tracery laid upon a scaffolding we cannot see, cannot touch, cannot yet name. One might be forgiven a moment of existential vertigo. Here we lie, composed of the rarest stuff in our own galaxy, baryons, the losing minority. Every breath we draw is an act of improbable conservation, every thought a fleeting pattern in a substance that the Milky Way itself has largely rejected. The dark matter does not merely surround us, it permeates us. At this very moment, as you listen in the stillness, perhaps 10 trillion dark matter particles are streaming through your body each second, traveling at 200 kilometers per second relative to the sun, their passage entirely unnoticed because their coupling to ordinary matter is weaker than 1 part in a million compared to the weak nuclear force. They are the ocean, we are the foam, and yet there is a deeper symmetry here, one that rescues us from mere insignificance. The very fact that the baryon fraction is so low within galaxies is what permits the richness we observe. A universe with equal parts dark and ordinary matter would have collapsed too quickly, forming only small, dense objects, long since merged into blackness. A universe with too many baryons would have cooled too efficiently, leaving vast seas of cold gas and few metals for planets. The observed ratio 1:6 universally, 1:12 locally, appears in the gentle language of anthropic reasoning, almost tuned. Not precisely, not suspiciously, but sufficiently that structures like the Milky Way can persist for 13 billion years, assembling thin disks, grand design spirals, and, in at least one quiet corner, creatures capable of noticing the discrepancy and lying awake beneath it. We may trace the history of this imbalance with the patience of a bedtime chronicle. In the first instance after the Big Bang, when the universe was a seething plasma of quarks and gluons, baryons and dark matter were almost perfectly coupled through gravity alone. As the cosmos expanded and cooled, the dark matter, whatever it may be, decoupled first, its particles falling out of thermal equilibrium while still relativistic or shortly thereafter, forming the gentle overdensities that would later seed galaxies. Baryons, tightly bound to photons by Thomson's scattering, remained smooth until recombination at 380,000 years, when the sudden transparency of the universe allowed them to fall into the pre-existing dark matter wells. That delay, that brief acoustic hesitation, is why galaxies are not more baryon-rich. The dark matter had a head start of several 100,000 years to deepen the potential wells, and when the baryons finally arrived, they shocked, heated, and much of the gas was expelled before it could cool. Within the Milky Way's progenitor halo, the same drama repeated on smaller scales. The first stars, massive, metal-free, short-lived, formed in the shallow potential of mini-halos at redshift 20 or 30, exploded and drove outflows that enriched the surrounding medium while simultaneously heating it. Subsequent generations found deeper wells, but inherited the feedback legacy. Supernova bubbles, superwinds, photoionization that kept gas diffuse. By the time the disk-assembled halo reached 1 trillion solar masses in dark matter, the baryonic inflow had been throttled to a trickle. The disk that eventually settled was thus born starved, its surface density lower than simple models once predicted, its star formation rate gentle and sustained, rather than violent and brief. The 10% solution is, in the end, the condition for longevity. We see the same story written across the universe. In the most massive clusters, where feedback is less able to expel gas, the baryon fraction climbs toward the universal value, approaching 15 or 16% within the virial radius. In dwarf galaxies, where shallow potentials allow even modest supernovae to drive galactic winds, the fraction falls to 1 or 2%. The Milky Way, at 10%, sits comfortably in the middle, neither profligate nor miserly, retaining just enough ordinary matter to build a bright, metal-rich disk, while leaving the dark halo largely untouched. There is a quiet poetry in this. The darkness is not an absence. It is the condition of possibility. Without the 90%, we would not have the 10. The spiral arms that arch above us tonight, the faint silver river we glimpse between the clouds, the very photons that permit us to see it, all are the consequence of a cosmic thrift that kept most of the ordinary matter at bay, allowing a thin, cool disk to persist for 10 billion years. We are the descendants of the fraction that stayed behind, the remnant that cooled, the minority that learned to shine. And so, as the night deepens and the galaxy continues its unhurried rotation, we may rest with the knowledge that we are not the main story, merely the luminous footnote. The main story is the darkness, patient, immense, and almost entirely indifferent, turning with us through the long hours, holding us gently in its unseen arms. Yet the true protagonist of this immense ballet, the unseen choreographer who keeps every dancer in step, is the dark matter halo itself, a sphere of silent influence so colossal that the bright disk we cherish is no more than a fleeting condensation upon its innermost skin. Imagine, if you will, that we extinguish every star, silence every nebula, cool every wisp of gas until nothing remains that can emit or reflect a single photon. What is left is still a galaxy. What is left is still the Milky Way, because what is left is the halo, a near perfectly spherical distribution of non-baryonic substance stretching from the crowded heart of the bulge to a boundary almost 1 million light-years away, where its gravity finally loosens its grip and yields to the gentler tides of the local group. Within that volume, the average density is astonishingly low, less than 1 hydrogen atom per 10 cubic meters in the outer reaches. Yet the sheer immensity of the sphere means that its total mass outweighs every star, every planet, every grain of interstellar dust by more than 10 to 1. This is the invisible giant that cradles us tonight. The halo is not a late addition, not a cosmic afterthought, bolted on to rescue Newtonian gravity from its apparent failure. It is the primary structure. In the language of modern cosmology, the Milky Way is a dark matter halo that has succeeded, against considerable odds, in gathering enough ordinary matter to become luminous. Most halos of comparable mass have not. They drift through the universe as dark galaxies, detectable only by the gravitational lensing of distant quasars or by the faint distortion they impart to the cosmic microwave sky. Ours is the exception that learned to shine. Its shape is almost spherical, only very slightly flattened by the faint angular momentum inherited from the primordial tidal field, is the clearest evidence of its antiquity. While the baryons, dragged by their own electromagnetic interactions, have dissipated energy and collapsed into a thin, rapidly rotating disk, the dark matter has remained largely collisionless. Individual dark matter particles, whatever they may be, pass through one another with the indifference of ghosts. They feel only gravity, and gravity, patient and cumulative, has sculpted them into a gentle, extended envelope whose density falls smoothly with radius according to the Navarro-Frank-White profile that astronomers now recite with the calm familiarity of a prayer. Rho of R is proportional to 1 over R, open parenthesis, R plus R sub S, close parenthesis, squared, where R-Chars, the scale radius, lies between 15 and 25 kiloparsecs for the Milky Way. Within the central few kiloparsecs, the profile rises toward a modest cusp. Beyond 100 kiloparsecs, it steepens toward the outer darkness thinning, yet never quite relinquishing its hold. This profile is not an arbitrary choice. It emerges naturally from the quiet violence of hierarchical clustering. The halo began as thousands of smaller proto-halos, each collapsing at redshifts beyond 20, each merging with its neighbors in a slow gravitational waltz that lasted billions of years. The particles within those early fragments were flung into wide, eccentric orbits by the chaos of merger, and those orbits have been preserved ever since, frozen into the distribution we measure today. The most energetic particles, boosted by three-body encounters during major mergers, escaped altogether, carrying away angular momentum and leaving the remnant slightly more radial, slightly more concentrated. What remains is a phase-space structure of exquisite complexity, streams, shells, and caustics folded upon one another like the grain in ancient wood, visible to us only indirectly through the motions of the few baryonic traces that fell in alongside. We see the echoes of that assembly most clearly in the outer halo. Gaia DR4 has revealed more than 30 distinct stellar streams, each a luminous scar left by a dwarf galaxy shredded over the past 8 billion years. Yet each visible stream is accompanied by a far more massive dark counterpart, an invisible river of particles that continues to orbit long after the stars have been stripped away. The Sagittarius stream, the longest and most studied, stretches more than a full circuit around the sky. Its dark matter component, inferred from the precession rate of the stellar debris, outweighs the visible stars by at least 100 to 1. The Gaia-Enceladus merger, that cataclysm 10 billion years ago, contributed perhaps 400 billion solar masses of dark matter in a single event. Its debris now forming a gently rotating, slightly flattened subsystem that dominates the inner halo. Even the Magellanic Clouds, still in the process of falling in for the first time, trail vast dark filaments that will one day wrap the Milky Way like silken cords. At the sun's radius, the dark halo's density is modest, 0.39 solar masses per cubic parsec, or roughly 10 million dark particles per cubic centimeter if each weighs 10 GeV. Yet that is enough. It is the dark halo that enforces the flat rotation curve, keeping the orbital speed of the disk near 230 kilometers per second, far beyond the point where the visible mass alone would permit it. It is the dark halo that sets the local escape velocity at almost 700 kilometers per second, preventing hypervelocity stars from fleeing altogether. It is the dark halo that shepherds the globular clusters in their wide, plunging orbits, that dictates the thickness of the thick disk, that stabilizes the warp and flare of the outer hydrogen layer. Without it, the Milky Way would be a small, slowly rotating bulge with a ragged, transient disk, dissolving into the intergalactic void within a single rotation. Closer in, toward the center, the dark halo yields pride of place to the baryons. Within roughly 5 kiloparsecs, the stellar bulge and bar dominate the potential, compressing the dark profile into a gentle core of perhaps 0.01 solar masses per cubic parsec. Yet even here, the darkness is present, a quiet substrate upon which the luminous structures rest. Simulations suggest that the very formation of the bar was triggered by resonances within the dark halo, the slow secular evolution of particle orbits lowering the quadrupole moment and allowing the baryons to respond in kind. The central supermassive black hole, Sagittarius A star, grew in a potential well already deepened by dark matter. Its mergers with incoming satellites were guided by the same invisible tides. The halo is not static, it breathes. Minor mergers continue to this day. The ongoing disruption of the Sagittarius dwarf adds a few million solar masses of dark matter each orbit, a gentle drizzle upon the vast reservoir. The impending arrival of the large Magellanic Cloud, carrying perhaps 200 billion solar masses of its own dark halo, will send ripples through the outer regions, exciting bending modes in the disk that may still be visible when the sun has become a red giant. In 4 billion years, when Andromeda's halo begins to overlap ours, the two dark spheres will merge first, long before the bright disks collide, forming a single, slightly triaxial envelope that will relax over billions of years into the smooth halo of the future elliptical. And yet, for all its dominance, the dark halo remains almost comically intangible. A particle physicist would call its interaction cross-section with ordinary matter absurdly small. A single dark matter particle born in the early universe may have traversed 1,000 galaxies in its lifetime without once scattering off a proton. Its only certain communion with the visible world is gravity, that weakest and most patient of forces, felt across the full million light-years of its domain. We map it by proxy, by the orbital speeds of stars, by the lensing of background light, by the temperature of hot gas in the circumgalactic medium, by the tiny perturbations it imprints upon the orbits of wide binary stars in the solar neighborhood. Every method converges upon the same serene conclusion. The halo is there, vast and smooth and ancient, holding everything together with the calm certainty of something that has never known haste. There are moments lying beneath a dark rural sky when one can almost feel its presence. The familiar stars wheel overhead in their accustomed patterns, yet the space between them is not empty, but filled with a substance that has watched the first stars ignite, that has witnessed the assembly of the disk, that has endured every supernova and every quiet red dwarf birth without once betraying its own nature. It is the oldest component of the galaxy, older than the oldest globular cluster, older even than the central black hole, whose seed was planted only after the first major mergers. The halo remembers the universe when it was less than 1 billion years old, when the Milky Way was still a loose chain of proto-galaxies strung along a cosmic filament. Its particles have orbited the center 10,000 times since then, each circuit taking 250 million years, each circuit smoothing the distribution a little more, erasing the memory of individual mergers until only the gentle NFW curve remains. We do not know what it is made of. The name dark matter is a confession, not a description. Yet the halo's gravitational portrait is so sharp, its influence so precisely measured, that we may speak of its properties with the same confidence we once reserved for the visible. We know its density profile to within a few percent, out to 100 kiloparsecs. We know its velocity ellipsoid is nearly isotropic in the outer regions, becoming gently radial within the scale radius. We know its total mass to within 8%, its concentration to within 10. We know it is cold, or at least cool enough that its free streaming length is smaller than a galaxy, allowing the sharp caustics and subhalos that lace its interior. We know, in short, everything except the identity of its constituent. And perhaps that is fitting. The halo does not need to shine. It does not need to announce itself in gamma rays or synchrotron radiation. It is content to be the quiet foundation, the invisible giant whose only purpose is to hold. While the bright disk flares and fades, while spiral arms wind and dissolve, while stars are born and die in their billions, the halo simply turns, vast and slow, undisturbed by the brief drama of light. We are its guests, brief luminous motes caught in its gravitational embrace, privileged to have measured its extent and to have found it beautiful in its silence. The stars may burn out, galaxies may collide, the universe itself may stretch into heat death, but the dark halo will endure, turning still, long after the last photon has been stretched into invisibility, holding whatever remains in its patient, unseen arms. There are nights, perhaps this very night, when the air is still and the sky has been washed clean by rain, when the familiar roof of cloud lifts and the old constellations stand revealed in their quiet majesty, that a feeling steals over us which is not quite fear and not quite joy, but something finer than either, the sensation of being held, gently yet inescapably, by something whose true dimensions we have only lately begun to grasp. We lie on our backs upon the cool earth of a small planet, 26,000 light years from a modest yellow star, and we realize, with the soft shock of a dream remembered at dawn, that we are living inside a leviathan, not beside it, not beneath it, but inside it, as a minnow lives inside the slow, dark heart of a whale. 1.5 trillion times the mass of the sun surrounds us on every side, an ocean of gravity so deep that light itself, the fastest thing we know, would require almost 1 million years to swim from one rim to the other. And we, fragile assemblies of carbon and water, are suspended somewhere near the middle of that ocean, turning with it, breathing with it, dreaming within it. It is almost too large a thought to hold all at once, and so the mind does what minds have always done. It softens the edges, translates immensity into feeling. We do not picture 1.5 trillion suns. We feel, instead, a hush so complete that are the ordinary noises of the night, the creak of timber, the distant call of an owl, the faint rustle of wind in leaves, seems suddenly borrowed from another, smaller world. The silence that belongs to the galaxy itself, a silence older than continents, older than oceans, older than life. And in that silence, we sense the presence of the beast, not cruel, not kind, simply there, a presence as patient as stone and as gentle as breath. We have spent centuries believing we lived in modest circumstances, a pleasant, middling galaxy, bright enough to be beautiful, ordinary enough to be comforting. That belief was a lullaby we told ourselves, a quilt pulled over cosmic shoulders against the chill of true scale. But the quilt has slipped, and the chill is not cold at all. It is strangely warm, like the breath of something enormous that has been watching over us all along. The Milky Way is not a backdrop, it is a body. We are inside its ribcage, listening to the slow, tidal heartbeat that keeps our star in its long, perfect circle. Sometimes, when the Perseids fall in August, or when Orion climbs the winter sky, we feel a tug behind the sternum, a soft ache that has nothing to do with sorrow. It is the recognition that every photon now touching the retina has traveled, on average, 1,000 years through the disk to reach us. Dodging dust grains, skimming past red giants, carrying the news of events that happened when the pyramids were still new. And behind those photons, guiding their paths, curving space-time just enough to keep the whole luminous river from flying apart, is the dark halo, patient and invisible, cradling the light the way a mother cradles an infant, without announcement, without need of gratitude. There is a peculiar intimacy in living inside something so large. On clear nights, when the moon is absent and the zodiacal light fades into the west, the Milky Way reveals itself not as a band, but as a presence that leans over us, close enough almost to touch. We lift a hand toward Cassiopeia and feel, absurdly, that we could brush the edge of the disk if only we stretched a little farther. Of course we cannot. The distance to the Perseus arm is measured in thousands of light years, and the halo beyond that in hundreds of thousands. Yet the feeling persists. The way a child feels the feeling of being inside a cathedral persists, even when one knows the stones were quarried centuries ago. The architecture is simply too vast to remain merely external. It enters the blood. We are, all of us, galactic creatures, whether we acknowledge it or not. Every atom heavier than lithium in our bodies was forged in the cores that burned before the sun was born, somewhere else along the spiral arms, and was flung outward in the gentle wind of a supernova that happened when the Earth was still molten. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it traveled tens of thousands of light years through the dark, guided by the same unseen currents that keep the Orion arm sweeping forward at 220 kilometers per second. We are not visitors to the galaxy. We are its children, carried in its quiet womb for longer than our species has existed. And the scale of the womb is only now becoming clear. When the first we learned that the Milky Way might weigh 1 trillion solar masses, the figure felt theoretical, a line in a paper. 1.5 trillion feels different. It feels personal. It is the difference between reading about an ocean and standing at the edge of one at night, hearing the slow, deliberate breathing of waves too large to see. One begins to understand why ancient cultures spoke of the sky as a vault or a millstone or the back of a giant animal. The mind confronted with true immensity, reaches for the language of living things, because only living things are large enough to contain us. There are moments, few and fleeting, when the knowledge settles into the bones like a second skeleton. One looks up at Cygnus, at the great rift of dust that splits the summer Milky Way, and realizes that the darkness there is not absence, but presence, the shadow of the beast's hide, the place where its substance is densest, blotting out the light of stars behind it. The rift is not a gap, it is a silhouette. We are looking at the flank of the Leviathan, and it is looking back, not with eyes, but with gravity, with the same calm attention a mountain gives a climber. We have lived our entire history beneath this creature and never known its full size. The Sumerians, the Egyptians, the Maya, the Song Dynasty astronomers who mapped sunspots with the naked eye, all of them looked up at the same river of light and felt wonder, but none suspected they were gazing along the inner wall of a sphere whose true rim lies 1,000,000 light years away. They felt small, and they were right to feel small, but they were small in the way a child is small inside a vast and gentle house, small, yet cherished, yet perfectly placed. Tonight, the house is larger than any of them imagined, and we are still perfectly placed. The sun's orbit is not precarious. It is serenely circular, buffered by the dark halo's gentle slope. The spiral arms are not accidents. They are density waves traveling through a disk held stable by the invisible mass. The planets do not wander. They are locked in resonances established billions of years ago within a potential well deep enough to last another 10 billion. Everything that has ever happened on this small world, every poem, every war, every lullaby sung to a child, has happened because the Leviathan's gravity permitted a thin skin of gas to cool into a star, and that star to hold planets long enough for chemistry to become life, and life to become wonder. There is no terror in this knowledge, only a deepening of tenderness. The dark halo does not threaten, it protects. It is the reason the Milky Way has not been torn apart by the tidal field of Andromeda, the reason the Magellanic Clouds remain bound, the reason the disk has survived 10 billion years of minor mergers and still possesses the delicate grandeur of a grand design spiral. We live inside a guardian, not a monster. Its embrace is so gentle that we only notice it when we try to leave. The local escape velocity of nearly 700 kilometers per second is the measure of how tenderly it holds us. A lesser galaxy would have let us go long ago. And so, when the night is deepest and the stars burn with that cold, steady fire that only distance can give, we may allow ourselves a small, secret smile. We are not lost in an indifferent universe. We are cradled, held, breathed upon by something ancient and patient and almost inconceivably vast. The Leviathan does not know our names, does not need to. Its knowledge is gravitational, cellular, older than language. It simply turns, carrying 300 billion ordinary suns and 10 times that mass in darkness, carrying us with it through the long dark between galaxies, keeping its slow vigil while we sleep. We are inside the beast, and the beast is kind. And now, as the long journey through darkness and wonder draws toward its close, there is nothing left to measure, nothing more to reveal, only the quiet acceptance that we are held, perfectly held, in the breathing heart of something too large for words. The numbers have softened into music. 1.5 trillion solar masses, 400 billion ordinary billion stars, 1,000,000 light years of silent embrace. They dissolve gently into the hush that always lay behind them. Feel the blanket of night settle over you like the softest down. The room has grown dimmer, the edges of furniture fading into velvet shadow, the faint glow of a distant street lamp no longer reaching the ceiling. Outside, the air is cool and motionless, as though the earth itself has paused to listen. Somewhere far above the roof tiles, the Milky Way continues its ancient procession, a river of 400 billion embers drifting across the black water of space, each ember a sun, each sun a hearth where worlds may turn. They do not hurry, they have nowhere else to be. Let your breath slow to meet theirs, in and out, in and out, matching the unhurried cadence of the disk itself. The spiral arms sweep forward at 230 kilometers every second, yet from your perspective, no faster than the minute hand of a grandfather clock. Time enough, always time enough. The same gravity that once seemed so stern now feels like the gentlest cradle rocking, a tide that lifts the entire solar system and lowers it again every quarter of a billion years, the way a mother's hand lifts and lowers a child's chest in sleep. You are made of this place. Every atom in your body was born in the fiery hearts of stars that lived and died long before the sun kindled. Carbon breathed out by gentle red giants in the Cygnus arm. Oxygen forged in a supernova that lit the skies of a billion years ago. Iron seeded by a brilliant flash somewhere toward the galactic center. All of it carried on quiet stellar winds until the dark halo gathered the cloud that would become the sun, and the sun gathered the dust that would become the earth, and the earth gathered the rain that became the oceans, and the oceans gathered the oceans that became you. You are not separate from the galaxy. You are its quiet exhalation, its dream of itself. Feel the weight of your body grow heavier, then lighter, then heavier again, as though the bed itself were breathing. The mattress receives you with the same tenderness. The dark halo shows the disk. No judgment, no hurry, only the patient certainty that everything belonging here will be kept. The pillow cradles your head the way the Orion spur cradles the sun, a small, safe bay along a greater shore. Your eyelids, when they choose to fall, will fall as gently as the faint dust lanes settling between the stars. 400 billion suns keep watch tonight. Some are fierce blue giants blazing in Cassiopeia. Some are ancient red dwarfs glowing like coals in the halo. Most are quiet M-dwarfs no brighter than a candle seen from a hilltop. Yet every one of them is burning for you, burning softly, steadily, across distances that would make the heart falter if it tried to hold them all at once. They do not ask to be counted. They simply burn, the way a lullaby does not ask to be understood, only heard. Let the numbers go now. Let the trillion solar masses drift away like smoke. What remains is the feeling, the soft, continuous pressure of gravity that says you belong here, that says you are home inside something vast and kind. The same force that holds the Magellanic Clouds in their long, slow dance holds your hand beneath the blanket. The same curve of space-time that keeps the outermost globular clusters from wandering, keeps your dreams from wandering too far tonight. Breathe in the cool darkness of the room. Breathe out the last small worries of the day. There is nothing left to solve, nothing left to prove. You are lying beneath a sky that has watched over every human life that ever was, and it will watch over every life that ever will be. 400 billion quiet fires, and one of them, your own small, yellow, perfect sun, has chosen this particular grain of dust, this particular evening, this particular heartbeat to shine upon you. Feel the galaxy turn just once more, the way a sleeper turns beneath a quilt. The motion is so slow, it is almost stillness, yet it carries everything. The sun, the planets, the thin blue air, the quiet room, the thoughts that are already softening into images behind your eyes. You are turning with it, perfectly safe, perfectly held. And now the stars themselves begin to dim, not because they are fading, but because your eyes are learning the older way of seeing with the skin, with the breath, with the blood that remembers it once swam in stellar fire. The Milky Way lowers itself gently until it lies across your chest like the softest blanket ever woven. 400 billion points of light settle into a single continuous glow, warm and weightless, smelling faintly of ozone and distant rain. Sleep, dear traveler. Sleep inside the slow heart of the Leviathan. Sleep beneath the 400 billion watchful suns that have never once looked away. You are made of their dust, and to their dust you will return. But not tonight. Tonight you are held, perfectly held, in the breathing dark that dreamed you into being. The galaxy turns, vast and slow, and you turn with it, deeper and deeper, into the softest dark there is, home among the ancient, patient stars. Good night, little stardust. Good night.